Okay, I want to welcome all of you. I think you know who I am, but I'm Roger Wakimoto, currently the president of the American Meteorological Society, although technically I am past president because that happened on Sunday. But symbolically, it really doesn't happen till the end of Wednesday banquet when you'll see me stumble off the podium because I'll be so tired after all the effort. You're here because of me. So let me just say that right away. And by the way, I'm incredibly pleased because this is new, and anytime something's new, you're never sure how many people will come, and I'm hoping it'll grow. So what's going on is the student conference is just enormously successful. It's one of the things that I and many other people just brag about. But you're off on the side. And it was my vision to say, I want to bring you into the mainstream of the annual meeting. I want to give you guys a forum to try to attract as much of the members that are here during the main part of the week so they can come and hear you and you can brag about your work. I knew, but then I stepped away. I knew the student leaders would think of very clever ways of selecting the papers, which they did. If this goes really well, and if you really like it, please let us know because we would try to think of ways to expand it. But you never want to do something big. You test the waters first to make sure it's working well. So I'm as anxious as you to, hope you don't get nervous, but I'll be sitting in the front. I'm as anxious as you to listen to today's presentation, and with that, I'll turn it over to the chairs.
Thank you, Dr. Wakamoto. Our first speaker today is Juliana Glinskis. Juliana comes from LeTourneau University, and she actually just graduated a couple weeks ago, so congrats on that. And she graduated with a degree in chemistry and minors in math and physics. And she'll be speaking today about verification analysis of red flag warnings in Nevada.
Well, good afternoon and welcome to my presentation. I wanted to start off and give just a short little background about who I am. I'm originally from Modesto, California, which is how I ended up working and volunteering with the Weather Service in Reno, Nevada. And so I got to do research with them as well as launching the weather balloon, which was a lot of fun. So to give an overview, this is the county warning area for the Weather Service in Reno. And this warning area is divided up into fire weather zones that are outlined in black. Now, each of these has a number and is forecasted based on that number. Or the brown ones are in Nevada, the red ones are in California. So just to give an overview of the verification process, if the criteria is met and a warning is properly issued, it is considered verified. If the warning is issued but criteria is not met, it's unverified. And if criteria is met but the warning is not issued, it's missed. And my purpose was to look at the missed and unverified warnings. And there was a little bit of intrigue at the Weather Service because I am a chemistry major, I'm coming from the outside. And so they were kind of curious to see what my outsider perspective was. Did I have any recommendations for how they can improve the process and reduce the number of missed red flag warnings? So to kind of go into the process of how I did this, I started off looking at events from 2011 to 2017. As some of you may know, this was a huge drought for us. I also focused in on the months of June, July, and August, which are usually when fire weather starts to get going. So initially, I was looking for wind and humidity anomalies, and I was kind of looking for a correlation, but I kept hitting a brick wall, and it was kind of frustrating at times because that was initially the structure of the research I was doing. But then I had kind of an epiphany where I realized that forecasting involves predicting the future, and that seems a little bit basic, but I think oftentimes in research, we look at what happened and we forget that the forecasters don't know what actually happened. They're looking at the models, they're looking at what could happen. And so my goal from that point was to see if I could figure out the forecaster perspective instead of just looking at it, post-analysis. So I lucked out because the Weather Service in Reno writes really good area forecast discussions, and it actually is one of their most popular products. So they tend to write very detailed AFDs. So I developed a methodology around it where I started 2 days before a missed event. If there was another red flag warning event that happened, even if it was verified or unverified, I expanded it out because I was trying to get the process leading up to the red flag warning to see if there was a change in their opinion, if there was a change in how they developed their system. And so I usually excluded dry thunderstorm events because those are extremely unpredictable, but if they were within the range of the missed red flag warning event that I was looking at, then I included them for analysis purposes. So to go into my results, I compiled all the data and I found that for missed events only, borderline and marginal conditions were the #1 factor. This is where criteria almost met but didn't met. In Reno, relative humidity has to be less than 15% and winds have to be over 30 miles an hour, and those conditions have to sustain for at least 3 hours. Those conditions are not always met, and sometimes the forecasters would think that humidity wouldn't recover overnight and then it would bump up at the last minute. And so that's where you got a lot of those missed events. The other one is overshadowed by another event. There were a few instances that I read in the AFDs where forecasters knew that within 3 days of the missed event, there was going to be a more severe event. And because they were trying to reduce warning fatigue, they would specifically decide to hold off on issuing a warning just so that they could focus on the more severe event. So that was really interesting for me to discover. When looking at the unverified event analysis, there's a huge elephant in the room with the overwarn due to fire behavior. This is where forecasters would issue a red flag warning even if they weren't sure if conditions would meet. And the reason why is because there was extreme fire activity already occurring either in their CWA or nearby. And so a lot of times forecasters would debate, do I issue the warning because it's going to verify, or do I issue it because there is a real and present threat? And so sometimes it wouldn't meet criteria, but it was still a necessary thing to help the public know there's a danger for fires. I combined these two together, and as you can see, when you combine them together, marginal and borderline conditions are definitely the #1 cause, with overwarn related being the second one. Some interesting analysis, Zone 450, which is where the Weather Service in Reno is located, it statistically accounted for the greatest number of missed warnings. It also accounted for the highest percentage of warnings in general for any zone in the CWA. This was kind of an interesting thing to discover. The lowest percentage of verified red flag warnings is Zone 278, the highest is 271. And it's interesting that they are right next to each other, and it kind of shows the challenge that the forecasters are dealing with, where it's like sometimes changes can happen so quickly across different zones that one zone may not necessarily be more easy to forecast for, but it just happens to have more verified warnings than the one next to it. So another thing to note is the month with the lowest percentage of verified warnings was in August. The highest percentage is in June. My guess personally is that in June they're coming into fire season, so they're getting used to it, and things kind of get a slow start in June. By the time you get to August, fire behavior is rapidly intensifying, and so it might be a little bit less easy to predict exactly when the fire conditions will be at the worst. What I did find interesting is almost all the missed red flag warnings were confined to one event. So it's not like the Weather Service was missing multiple opportunities. It was usually that one opportunity that they just had trouble with. And so that's kind of an interesting aspect. Overall, the Weather Service in Reno had about a 63% success rate, which I think for the topography and the complexity of the dynamics in their CWA, that was a pretty good result. So to kind of wrap things up a little bit, most events are missed because they're either overshadowed or due to the marginal conditions. And this concern is especially amplified when the models don't agree. There were a lot of times where forecasters would specifically say that the NAM or the GFS was contradicting one another, and they weren't sure if the front was going to come into their area or if it was going to be just to the north of them. And it was very clear that they are very concerned about warning fatigue. You have a desert region like Reno, and fire conditions can happen at any time in the year, but they don't want to overwarn because then people are going to stop listening to them. And so it's trying to find that fine balance between issuing warnings and making sure you don't overdo it. So one thing that I definitely want to pass along is that well-written AFDs are crucial for verification analysis when you're trying to look at the forecaster perspective. It's very important to be able to look through and get that forecaster insight, because a lot of times forecasters are not going to remember what they did on July 6, 2011. So this was a nice way to kind of snapshot and say, this is their thought process, this is what they were going through, and then use that to then go into the future and decide, well, how do we fix that from going in? So the part where I was asked to give the outsider recommendations, I kind of divided it into two categories, idealistic and realistic. Idealistic is kind of the pie in the sky. This, if everything would come together, this would be ideally what we would want. The first one is forecaster model improvement. Obviously, as the forecast models improve, you're not going to have as much debate over the marginal and borderline conditions, because forecasters are going to be able to hypothetically tell, is it going to meet criteria or not? The second one is the ideal that everyone would take warnings seriously, such that forecasters could feel more at ease when they're issuing this, knowing that they're issuing just on the basis of on fire conditions. And the last one is that people need to stop creating wildfires. Wildfires in the West are mostly human caused, and that's an element that no forecaster can ever predict. So in terms of the realistic improvements, I recommended that they allow some flexibility in the criteria. There's a hard line at 15%, but some fires do not care if it's 30%. If the fuels are already dried out and a spark happens, that fire is going to take off and it's going to be a huge concern. So I recommended kind of allowing a little bit of flexibility given the situation. The other one is modifying the fire zone boundaries. As you may have seen earlier, they're very big and they cover a very complex terrain. This is realistic, however, it is a very long and slow process, mainly because of the politics of the region. You have to get multiple agencies to agree on modifying these zones. So it's realistic, but probably won't happen anytime soon. And with that, I would like to thank my friends at the Weather Service in Reno for their help, and I will now take questions.
Thank you, Juliana. We have time for a couple questions. Please either step up to the mic or project your voice.
Hi, my name's Chuck Hackerainen. I'm retired from the Electric Power Research Institute in Palo Alto, California. You mentioned two criteria they used, persistence of low humidity, persistence of winds in excess of 30 miles an hour. Both of those are meteorological criteria. Do they include any non-meteorological criteria, such as existing soil moisture or antecedent existence of a freak snowstorm in June that might also suppress the fire danger, but might not suppress the meteorological conditions that could lead to fire?
So for verification purposes, it's solely based on those meteorological conditions. Now, when you talk about a freak snowstorm or a freak cold spell, that's kind of taken into the forecaster discernment, where they say, it's going to be too cold to create fire conditions, because even in the winter, you can have similar conditions, but, fires aren't going to start. So at that point, it would really be at the discretion of the forecaster to issue it. But in terms of verifying it after the event, those are the criteria that they use to determine if it was good or not.
Do we have any other questions? No? Let's thank Juliana again. So next up is Harag Najarian. He comes to us from UC Davis, where he graduated last September with a Bachelor's of Science in Atmospheric Science. He'll be speaking to us today about some work that he presented during the student conference as well. And I'll wait for the title to come up because I don't have it off the top of my memory, but it has to do with thermodynamic response of tropical convection. So thank you for getting that pulled up before I made a fool of myself.
Because I don't want to present, but like presenter with notes. I think that's all that we can do up here. Okay. Oh, I have a bunch of notes, I think. Okay. So do you want to know how to do with the notes? Because I have a Mac that I'm not familiar with this. Thank you for that introduction. So, hope everyone is having a great time here at the Convention Center, or as I like to call it, the Convection Center. During my senior year at UC Davis, I worked under Matt Eigel in order to better understand the tropics as a whole. Our goal was to try and better understand the links between tropical moisture and precipitation. This figure shows satellite observations of precipitable water. What you can see is that over the tropics it's very moist, yet we know that precipitation is quite uncommon. What I initially focused on in my research is relating that observed relative humidity to observed precipitation, but ended up shifting my focus to analyzing model data and cloud processes. But before we dive into the methods, let's take a look at something familiar: precipitation in the tropics. As we all know, the Hadley cells has a huge effect on tropical precipitation. The Hadley cell provides the thermodynamics and the dynamics through the returning branches of the cell. We know the Hadley cells are a good source of constant convergence, but moisture, however, is highly variable. One relatively easy way to predict precipitation in the tropics is by observing the moisture in the atmosphere. Now, this can be done through various ways. Most particularly are done through radiosondes and satellite data. Now, the method in which we'll be measuring moisture content is going to be in the atmosphere is going to be through column relative humidity. So column relative humidity is essentially calculated by taking the observed moisture content in the free troposphere and dividing it by the moisture content of a saturated atmosphere. Now, previous observational studies that utilize satellite data and station data have shown the relationship between column relative humidity and precipitation to be an exponential relationship. Now, before we start testing theories, we need data to work with. But most importantly, we need data that match previously observed results in order to be confident in that said data. So in our investigation, we utilized a dynamo field campaign over the Maldives. Weather balloons were launched every 3 hours between the months of September through February. Data was logged every 2 seconds, and the 3 variables that we'll be interested in is temperature, relative humidity, and pressure, as well as radiosonde data. We're also receiving station data at the launch site, which provided us precipitation data by the minute. Okay, let's take a look at how our data matched up with previously observed results. Now, as you can see, there is a correlation with that and exponential relationship. However, we do see that drop off near the end. Due to the atmosphere not frequently reaching the 90 to 100% column relative humidity, the lack of data was essentially causing that drop off. So now that we are confident in our data, and we can now move on to the observable application of the 2-layer theory, which I'll get to right now. Now, the 2-layer theory suggests observing the atmosphere into 2 separate columns rather than just one. By splitting the atmosphere at the freezing point, which is around the 4-kilometer mark in the tropics, we end up being able to relate precipitation intensity directly to various different cloud types. Now, this helps in aiding predicting Earth's radiative balance more accurately. Now, in order to do this, we follow the same steps as before, but instead, there's a little twist. We take the lower layer of the moisture content and we divide it off. Oh, you can't see my cursor, okay. We divided it off by the saturated atmosphere. And we do the same for the upper layer. And just for familiarity, we can take the upper column relative humidity and add it together with the lower column relative humidity and get that original column relative humidity. Now let's see how our data matched up with simulated results. So this graph we're looking at represents the lower layer RH in the x-axis, the upper layer RH in the y-axis, and contours represent precipitation intensity, violet being the lowest, yellow being the highest. Now, the observational results were not quite exactly what we were looking for. Unfortunately, the field campaign just not simply provide us with enough data close to comparing a simulation with millions of convective plumes to work off of. So our initial results didn't quite work, but I didn't want to stop there. I wrote a script to implement over over 700 observed profiles of the atmosphere into a cloud resolving model. You heard right, over 700 simulations. This unorthodox way of using models will test the response of RAMs to moisture by comparing simulated precipitation events with observed events. So now let's take a look at the model specs before we get into our results. So I ran our simulations through version 6.2.08 of RAMs, which includes a unique mechanism of lift, which I'll get to in a little bit. Now, we're using grid spacings of 68 by 68 by 65 with 750 meter horizontal spacings and up to 500 meter spacings in the vertical. So we initialized our model with observed profiles of temperature, relative humidity, and pressure. And the mechanism of lift we actually used to create convecting clouds is a new addition to RAMs, specific to this version. And it's much more of a realistic application compared to the warm bubble technique previously used, which would end up altering the integrity of the thermodynamic profile. So we ended up applying a well-examined convergence value at the center of the model surface. This force remained constant for the entire duration, 1 hour. And we varied, after our initial results, we also varied our convergence values to include weaker values, which then came out to a total of 2,100 simulations. So just like the beginning of my presentation, we must first figure out if our model is behaving like nature. So we check the moisture to precipitation relationship first to see if it indeed is an exponential relationship. As you might notice, the results we got looked nothing like an exponential relationship, but rather a linear one. This was unexpected. I couldn't move past this result without further investigating, and this is where it got interesting. I took a step back and thought about the processes taking place in cloud formation. So when we think of a convecting cloud, we mostly imagine a thermodynamic feedback involved. Lifting the moist air parcel above the LCL condenses the air and heats up the atmosphere, lifting the air parcel even more, and continuing and continuing and continuing. Now, vertical velocity mostly depends on the thermodynamic feedback in that case. However, in our case, a large enough convergence value can essentially divorce thermodynamics from cloud formation and allow dynamics to control the convection. Now, vertical velocity highly depends on convergence intensity in our model's case. Now, I thought to myself, if I compare models that don't highly depend on thermodynamic process with ones that do, that would allow further investigation of the thermodynamics feedback in cloud convection. And that's exactly what I did. I ran two weaker convergence values over the same profiles, and by fitting the graphs with exponential curves, we can notice that by implementing a weaker convergence value, we end up with a more exponential relationship. The weaker convergence value we go. Quantitatively, we can see this through the trend of a rise in the exponential coefficient, which is really hard to see, but I promise you it does get higher as we get through the smaller convergence. So my initial hunch led me to an interesting hypothesis. I hypothesized that with weaker convergence values, the thermodynamic feedback relationship is more present and more apparent compared to when the lifting mechanism overpowers the natural response of convecting clouds. Now, it can be more apparent if we can actually visualize it. So by using state-of-the-art imagery funded by ClipArt, we notice that the large convergence value essentially wrings out the moisture in the atmosphere, while a smaller convergence value lets nature take its course, fundamental cloud processes to dictate precipitation rates rather than forced dynamics. Now, initially we utilized observational data from radio sounds and station data to replicate previous studies. Now that was important just to be confident in our data. We then moved on to test a two-layer theory which would better predict precipitation rates as well as various different cloud types over the tropics. When results turned out to be inconclusive, we moved forward by implementing the observed atmospheres into a cloud resolving model with various intensities of surface convergence. Now, after we investigated over 2,100 simulated precipitation events, we suggest that the exponential relationship is highly dependent on the thermodynamic feedback response in cloud formation. Now, for future work, continued analysis must take place in order to firmly tie this relationship, this exponential relationship between precipitation and moisture to the thermodynamic feedback. Some ways we can do this is by actually measuring the flux of the ascending branches of the Hadley cells specific to the dates of the launch sites, just to better control our data, our results. We can also utilize radar data to achieve even a broader view of precipitation rather than one Eulerian point of view. Now, some applications I thought of is actually applying convergence zones to analyze cloud properties and interactions more closely in models. Oops. And it also brings up the question of analyzing models by looking at numerous coarse simulations rather than one highly fine resolved simulation. And with that, my name is Harag Najarian. You can contact me through email or LinkedIn. And I want to thank you, AMS, personally, for allowing me the opportunity to present. And I'm truly humbled by that, and I thank you for your time.
We have time if anyone has a quick question for Harag.
Using your convective mechanisms, you can actually generate the clouds, but to make them precipitate to the ground, you're going to need cloud condensation nuclei on which the droplets can then grow to a size that they'll actually fall to the earth. Did you make any specific assumptions on the availability of CCN in your simulations?
With the model, I know that it was an idealized simulation, so I think we kept all the cloud condensation nuclei the same for all the observed profiles. Yes. But I don't know exactly the amounts and the distribution of the aerosols or of the nuclei.
But they weren't a limiting factor, basically.
No.
Was there another question behind? Yeah.
Perhaps, quick question about the statistics. It wasn't clear to me from what I could see with my limited vision that the exponential fit was better than the linear fit to data. So have you done an analysis that would convince me that this is the case? What is it?
Yeah, it was really hard to see. However, if you look at the exponential coefficient at, I can't point at it, but in those little boxes in the left-hand corner of each plot, if you look at actually, I would actually suggest you look at the last bullet point. There is a gamma in there, and that gamma would be increasing with smaller convergence for a better fit. So it is a better exponential fit. But yes, we do need to do more analysis and statistical.
Maybe looking at something like a root mean square error or a reduction of error statistic would, with some validation, would help you know that the
It's actually
more
exponential.
sophisticated model gives you better fit in a validated way.
Yes.
Thanks.
All right, let's thank Harag again.
Okay, thank you, Harag. Next up will be Colby Franck. That's Chelsea's, my bad. Colby, you're up next. Yeah, sorry about that, guys. So Colby joins us today from the Rochester Institute of Technology, or RIT. He's currently a senior, majoring in chemical engineering, and he will be talking today about trees, aerosols, and clouds. Thanks, Colby.
Hello, everybody. Thank you for joining me and listening to my talk. I am going to be presenting my work from this summer at Penn State's RU program.
You can just put it in the presenter mode, sorry.
And my work was on trees, aerosols, and clouds. So I was studying the effect of the changing aerosol composition on cloud formation processes in the northeastern United States. So the main motivation behind my project was that there are two major forces occurring in the northeastern United States right now, and that is a reduction in air pollution as well as an increase in trees. And there's an increase in trees as a result of people moving away from the countryside to the urban areas. So there's more trees being forested, as well as the fact that the urban and suburban areas are becoming more forested. Here you can see a graph reprinted from Daltrey that just shows the decreasing air pollution values for the northeastern United States. So in the 1990s, the major aerosols were from the nitrogen oxide compounds and sulfur oxide compounds, and these would react in the atmosphere to form the main pollutant of sulfuric acid and ammonium sulfate, which are the most common aerosols that we were think of in the past. But with the current aerosols, the trees would release alpha-pinene, beta-pinene, and isoprene, which would react. They're highly reactive compounds. They go into the atmosphere and they oxidize to form carboxylic acid compounds. So these are norphenogonic acid, pinonic acid, and penic acid. And these would be the main compounds that we'll be looking at for the study. So we'll be comparing the norphenonic acid to the sulfuric acid compound. So first, I had to look at Koller theory. And traditional Koller theory predicts the equilibrium size of a water droplet based on the concentration of the solute, as well as the solute's properties, and the curvature effect of the droplet, as well as the saturation ratio. But the problem with the traditional Koller theory is that it works really well for the inorganic, anthropogenic aerosols, but it doesn't work so well with organic aerosols because it assumes that the aerosols are highly soluble and that the concentration of the solute is pretty dilute. But for the organic aerosols, they are highly hydrophobic, so they don't really dissolve in the water, so you can't really use this, and we had to look at other forms of Koller theory. So this is a form of Koller theory from Raymond and Pandis, which treats part of the aerosol as insoluble. And the problem with this model to use completely is that it assumes a certain fraction of the aerosol is insoluble, but I wanted to have a model that would predict the solubility, or would predict the amount that dissolves and adjust accordingly to like the droplet growing in size. So I came across this model from Asawaku and Means, which treats the aerosol as a solid core that is at the center of the droplet. And as the droplet increases, more of the core is able to dissolve and away from the surface and diffuse out to the surface. And it's assumed that the time frame of diffusion is quick enough that you can ignore the time dependence of diffusion, which allows the aerosol to slowly dissolve as the droplet increases in size until there's enough water that it possibly would completely disappear and becomes into the water droplet. So I combined equations 1, 2, and 3 to derive equation 5, which looks pretty simple, but when you plug in equation 4, it becomes more complicated. And this, from here on, I will be calling equation 5 the modified Koller theory. Here you can see a comparison of traditional Koller theory to modified Koller theory for the 3 compounds. So the one is ammonium sulfate, which is the air pollution one, alpha-pinene, which is the particle directly released by the trees, and penic acid, which is the particle that would be oxidized from the alpha-pinene. So the main comparison here would be the ammonium sulfate to the penic acid. And you can see that for the ammonium sulfates, traditional Koller theory doesn't really differ that much from modified Koller theory, which is what you would want. And that for the alpha-pinene and penic acid, it requires a significantly higher saturation ratio to activate the droplets for the modified Koller theory versus the traditional Koller theory. The modified Koller theory was put into an air parcel model. So you have a volume of air with a known size and a given number of aerosols with a specific concentration distribution, size distribution of particles. And as the parcel rises in the air at a given updraft speed that's remained constant, there's adiabatic expansion and cooling, which creates the cloud formation, and you have the water droplets form. Here you can see the results of my for the air parcel model. I ran the air parcel model for various compounds, and they were the only compounds in the parcel with different size distributions that are known. So in figure A, you can see the initial size distribution of all of the particles. And right off the bat, you can see that the organic aerosols start out as a larger size than the organic species, and that's because the inorganics take up water more readily, so they just start out larger. And then for graphs B through G, they show the size distribution immediately after all of the water droplets that would activate to become cloud droplets have completely activated for the various updraft speeds ranging from 25 centimeters a second all the way up to 1,000 centimeters per second. And so for each of these size distributions, the band on the right of they're pretty straight up and down, and that's the water droplets. And the bands on the left are the unactivated cloud droplets, or we call them haze droplets. And so Koller Theory predicts that the larger aerosols activate more readily to become cloud droplets. And you can see if you look at figure B that the tail end of the size distribution, which are the larger particles, are the ones that activate to become shifted over to the cloud droplet size, leaving the other unactivated droplets on that side to be unactivated. And you can see that as the updraft speed increases, more and more of the particles are allowed to become activated. And this shows you that the organic species take larger updraft speeds to become activated, as well as the fact that the organic species are able to become activated for smaller sizes than the inorganic species. I just created a little table for you to see the comparison, so you don't need the graph. So the table shows the percentage of activated condensation nuclei droplets for the times in the figure, and the percentage given is it's just the percentage of those aerosols that became cloud droplets. And you can see that for the inorganic species, most of the droplets become cloud droplets pretty easily after 100 centimeters per second. And for the peonic acid, which would be the organic aerosols of interest, 74% becomes activated, so they do become activated. And once you hit 250 centimeters per second, it's about 90%. The alpha pinene doesn't really activate that well, you can see, but that's not really of major concern because they oxidize in the atmosphere anyways. And so the study basically tells you that oxidized monoterpenes, which is the peonic acid, actively promote cloud formation processes, but at a rate less than the industrial produced aerosols. And thank you for joining me. Any questions?
Thank you, Colby. Does anyone have any questions for Colby? Yep.
So if I understand your work correctly, the shift from man-made pollutants to natural terpenes in the Northeast should lead to less precipitation. And if that's the case, by how much less, and is it ever going to be something that could be physically detected through observations?
So this is an initial study to get funding to put this into a larger cloud model. So we haven't looked at that quite yet, but that'll be future work.
Are there any other questions for Colby? If not, please join me in thanking Colby. And last but certainly not least will be Chelsea Snide. Hopefully this is the right one. Correct. She is a senior currently in atmospheric science at the University at Albany, and today she will be talking to us about large-scale observational and modeling analysis of an unusual El Nino event.
Hi, and thank you for the introduction. So as he said, I'm going to be presenting about the unusual 2015-16 El Nino event and its implications for California precipitation. And I'd just like to acknowledge my advisors and co-authors, Drs. David Strauss and Dr. Eric Swenson from George Mason University. So to kind of give a little bit of background, here I'm showing the December, January, February, March seasonal average for sea surface temperature anomalies. So as you can see, on the left we have our 2015-16, in the middle 97-98, and on the right 82-83. And all of these can be considered significant El Nino events. So to kind of motivate this experiment a little bit, again, 15, 16 on the left, 97 in the middle, and 82, 83 on the right. And pictured here is the seasonal average for 200 hectopascal height anomalies. And in our 2015-16, I would like to note that we have a westward shifted Aleutian low indicated by the blue coloring, and we also have the subtropical highs in the orange and reds. And if you look close enough, our subtropical high actually extends into Southern California. And ultimately, this large-scale pattern that sets up is going to influence the jet stream and ultimately the storm tracks leading to precipitation. Unlike in 2015-16, our 97 and 82 El Ninos, our Aleutian low actually extends into Southern California, and our subtropical highs are more defined. So in these two instances, we have a different large-scale circulation that sets up than in 2015-16. So in the 2015-16, we saw drier than average precipitation, and a typical teleconnection for El Nino is wetter than average precipitation anomalies in Southern California. Because of the Aleutian low was shifted, our jet stream has also shifted, leading to the drier conditions in 2015-16. And just to motivate the experiment, this is important because the sea surface temperatures are going to give about changes in diabatic heating in each of these seasons. So we're hypothesizing that the diabatic heating is going to create different circulations. To just kind of show you what the precipitation looked like in each of these different years, we have 82, 83 on the upper left, 97, 98 on the upper right, 2015-16 on the lower left, and 2016-17 on the lower right. And just to note that in Southern California in 2015-16, we actually see a dry anomaly indicated by the red coloring. And these images are courtesy of Ben Cash at Koller. So moving on to look at what the diabatic heating actually looks like. Again, this is our seasonal average. On the left, we have our 2015-16. And on the right, we actually have our differences between the 2015 season minus the 1997 season. And as you can see in the difference plot, that there's significant differences between each year in diabatic heating. In 2015-16, we see a poleward shift in diabatic heating, and we see less meridional extent in the Eastern Pacific as well. And we hypothesize that these differences in the mean tropical diabatic heating between 2015-16 and other major El Nino events was the cause for the unusual dry conditions over California. Looking at the model error, this is the CFS V2 model minus the observations for the 2015-16 season. And as you can notice, there's considerable errors between the model and observations, specifically in the tropical region. And that the model actually produced a typical ENSO response when we looked at the diabatic heating, as well as the large-scale circulation, including the jet stream, the storm tracks, and precipitation. So kind of moving through our methods, we're going to do three different analyses. We have an observational analysis where we use our error interim 1979 to 2017 6-hour reanalysis. And for these, we are going to do all the DJFM seasonal averages. And for our kinetic energy field, we put it through a high-pass filter that's going to filter for days less than 10, so we can pick out our synoptic features. For our model reforecast, we use a 10-member ensemble. And for our ensemble, we just have 10 different initial condition starting dates. We're using both the NCEP CFS V2 coupled model as well as the CESM coupled model. And between these two models, we have a control reforecast, and we're doing our reforecast for the DJFM season for 2015-16, as well as the 2016-17 season. And lastly, we're going to do an added heating reforecast. And I'd just like to mention that we're comparing 2015-16 to the 2016-17 season because the 2016-17 season was a neutral year in respect to ENSO. So we're able to pull out some anomalies from the 2015-16 when we compare it to the neutral year. And lastly, because diabatic heating is not a measurable value and is not a parameter within the models, we calculate our diabatic heating using an estimation from the residual of the thermodynamic equation. So to kind of go into a little bit more depth about our model experiments, our control model computes our heating using the parameterizations of convection, radiation, and diffusion. And that's defined by the equation, the first equation above. So when we do our heating correction, we run our 10-member ensemble, evaluate the seasonal mean model heat, and we compare it to our error interim estimates of the seasonal diabatic heating. When we add in our heating, we add in an extra term. So in that second equation, we have a plus QA. That is going to be our added term to correct for the tropical diabatic heating. And because the model responds pretty strongly to this new term, we do this in iterations. So we take a fraction of the diabatic heating from observations, and we slowly add it into the model about 10 or 11 times to get a good estimate of what the correct observed diabatic heating looked like during that year. So moving on to our results, and I would just like to mention from here on out, all of these images are ensemble means. So this is our DJFM ensemble mean for zonal winds differences. So this is 2015 minus 2016 to extract our anomalies. Our observations are on the left, the CFS V2 control in the middle, and CFS V2 added heating on the right. And as you can see in the observations, we have a jet stream that dips equatorward and actually does not extend into California like it was expected to do. But in our CFS V2 control, we see that typical El Nino response where we have an extended jet stream into California, allowing for storms to track through this region. When we look at our added heating, we actually just see an amplified response to the control. So our jet stream both strengthens and it actually shifts poleward a bit, extending more into California than it did in the control. Looking at our high pass kinetic energy, this is a vertically integrated value. And I would like to note this is our indicator for our storm tracks. So in our observations on the left, we see a negative anomaly off the coast of California that actually extends through California in the, a little bit of the southern United States. And this is just a decrease in synoptic storms over Southern California, explaining the dry anomalies during this season. In CFS V2 control, interestingly enough, we don't see any strong positive or negative anomalies, and it can be argued that there might be a little negative anomalies in our storm tracks during this year, which was interesting because the model did produce above average precipitation in the control. But in our added heating, we see a strengthened anomaly in kinetic energy off the coast of California that actually does extend through the region, leading to more precipitation in this model as well. Lastly, I'm looking at precipitable water, and this is our total column. And I'd just like to note that this is similar to what the precipitation looked like in each of these experiments. So again, on the left, we have our observations. There's a clear negative anomaly over the Southern California and the Southern United States region. But in our CFS V2 control, we have a positive anomaly. In our added heating experiment, we see an amplified anomaly. So to kind of just summarize what we just saw in those results, the CFS V2 added heating actually amplified the typical El Nino response. So it failed to correct for the differences in the jet stream, the storm tracks, as well as the precipitation and observations, and we can refute our hypothesis. And I would also like to note we did this experiment for the CESM as well. It's just not pictured, but we did get the similar results, leading to our conclusion that it was just not model specific for this experiment. And in just a kind of quick conclusion, we saw this El Nino was unusual in the sense it didn't create a typical El Nino pattern in the mid-latitudes. So we saw that our low heights were shifted to the northwest, which was our Aleutian low, and we saw our less extensive jet stream. Our model heating did not, our model heating showed a typical ENSO response, and that in both our CFS V2 and CESM models, our added heating experiment did not improve the subtropical jet, the storm tracks, or precipitable water. So our observed dryness was not a signal caused by diabatic heating, and we hypothesized that some mid-latitude noise or signal played a larger role in the evolution of this El Nino event. And here are my references, and I would just like to quickly acknowledge the faculty, staff, and students at both George Mason University and University at Albany for all the support. So thank you.
Thank you very much, Chelsea. Does anyone have any questions? 4 out of 4. Let's do it again.
It's important, I believe, that students always be asked questions. I think you've shown in your analysis that there is no such thing as a typical El Nino. Everyone has to be considered someone on its own merits. I have heard, though, that because of the teleconnections theories, that there may actually be influences on El Ninos as to what's going on over even in the African continent at that time. And I don't see any analysis in your paper here. Did you actually look at what was happening in Africa to see what influence that might have explaining why this was not a, quote, typical El Nino?
Yeah, unfortunately, we did not analyze the African region, but we are extending the project to look at South America, and we also looked at the Indian Dipole region to see influences from the MJO and the Indian Ocean Dipole, but unfortunately, it didn't come up with any conclusive results. But I think that would be definitely a great idea to look at the African region as well, so thank you.
Any other questions for Chelsea? Okay, if not, then please join me in thanking Chelsea one last time. And also, please join me in giving one last massive round of applause to all 4 of our student presenters today. Thank you. I can assure you that Gage and Kenzie and I, as the co-chairs of the student conference, selected these 4 students from a pool of very highly talented students, and they were the best of the best. So thank you very much to all 4 of you for sharing your work with us. We hope, so this will conclude our session today, and hopefully we'll see this again next year as we continue to highlight the wonderful research being done by undergraduates. Thank you all for attending.
That's all good. Okay. That's good. Grab this out of your way.